Hey everyone, and welcome to our first of many videos about factoring. So in this video, we're not actually going to talk about what factoring is or how we factor polynomials. We're just going to talk about a tool we're going to come back to time and time again that's going to help us with factoring. So if you remember back towards the beginning of the semester, we talked about how you find the greatest common factor of integers, of just some numbers. And it turns out you can do the same thing with polynomial terms. So before we get into doing it with polynomials, let's recall how we do that with just the numbers. So for instance, I could ask you something like find the greatest common factor of the numbers 84 and 78. So we talked about a few different methods for doing this. I'm going to show you the method that involves using the prime factorization. I think it's going to shed some light on how we do the greatest common factor of some polynomial terms. So we would start by finding that prime factorization of both those numbers. So for instance, 84 could be written as 2 times 2 times 3 times 7. And similarly, 78, its prime factorization is going to be 2 times 3 times 13. And then using that prime factorization, the greatest common factor is going to be the product of all of the common prime factors. So all I want to do is I want to pick out the copies of everything that's the same. So for instance, they both have at least one copy of 2, so I'm going to add in one copy of 2. They also both have one copy of 3, so I'll add that 3 into my product. I'm not going to add a second copy of 2, right, because 84 has a second copy of 2, but since 78 doesn't have it, I can't include it. And similarly, 84 has that 7. Since 78 doesn't have 7 as one of its prime factors, I can't use that. And with that 13, the same thing. 78 has 13 as a prime factor, 84 doesn't, so I can't include it. So now I've gotten all the factors that they have in common. Right? Their product, 2 times 3, that's just going to be 6. So my greatest common factor of these two integers is 6. The process for finding the GCF of polynomial terms is going to look pretty similar to this. So when I'm looking for the greatest common factor of polynomial terms, I want to include two things. The first thing I want to include is the greatest common factor of the coefficients, right? The coefficients are just numbers. We know how to find the greatest common factor of those two numbers. The other thing we're going to include is going to be the lowest exponent of all of the variable components. So to help make this make some sense, we're going to do a few examples. So for our first example, let's consider the greatest common factor of 10x to the 5th y squared and 4x y to the 6th. So again, the first thing we want is the greatest common factor of the coefficients. So the greatest common factor of 10 and 4 is just going to be 2. And then the lowest exponent of all the variable components. So you'll see here, right, our first term has an x to the 5th that has 5 copies of x. Our second term just has 1 copy of x. So the thing in the greatest common factor is, again, the things they have in common. They have in common 1 copy of x. But all those additional copies in that 10x to the 5th y squared I can't include because my second term doesn't have them. And similarly with that y, if a y squared in my first term, a y to the 6th in my second term, well, they only have 2 copies in common. So I'm going to include that y squared as part of my greatest common factor. Let's consider an example where maybe the variables look a little different. Maybe we don't always have all the same variables. So for instance, I could ask you for the greatest common factor of 12x to the 7th with 18y to the 5th. So again, we just want to start with the greatest common factor of the coefficients. So the greatest common factor of 12 and 18, that's going to be 6. And then when we go to get those variable parts, you might say, well, I see an x to the 7th, I see a y to the 5th. Since those are they're the lowest, so I'm just going to throw both of them in there. But be really careful about that thought process. If we look at that 12x to the 7th, the number of copies of y it has is 0. Right? We can consider that term as 12x to the 7th y to the 0th power. So there's actually 0 copies of y on my first term and 0 copies of x on my second term. So the lowest possible exponent for both x and y is actually going to be 0. And we'll remember back from that exponent section, those both just turn into 1, and we're left with just that 6. right? You don't necessarily have to write out those x to the 0th, y to the 0th, but just know if they don't have those variables in common, you're just going to have the GCF of their coefficients. And one last example that kind of touches on a nuance from those GCFs of numbers as well. If I asked you for the GCF of 7x and 13yz, right? So 7 is prime, 13 is prime. They don't have any prime part of them that is common. So remember, that doesn't mean that they don't have a GCF. It actually means that their greatest common factor is just 1. So if you're ever looking at something and saying they have nothing in common, the GCF is going to be 1. Then similarly, because they don't have any variables in common, the first term doesn't have y or z, the second term doesn't have x, I'm not going to have any additional variable part, the GCF is just going to be 1. Alright, now that we've determined how to find the greatest common factor of some polynomial terms, we're going to show you what we actually want to be able to do with that. So we're going to want to be able to pull the GCF out of all the polynomial terms in a singular polynomial. So let's show you what that looks like. So let's use those two terms that we've already found the GCF of. So let's consider the polynomial 10x to the 5th y squared plus the term 4x y to the 6th. So we already know from the last page that the GCF of both of these terms together is going to be 2xy squared. So what we essentially want to do is we want to divide out that 2xy squared from both of the terms. So we want to be able to take that 10x to the 5th y squared plus 4xy to the 6th, and I want to take out that 2xy squared by dividing it. But doing that just on its own, right, that would totally change the value of the polynomial, and I don't want to change the value. So remember back from when we were trying to kind of change numbers around without actually changing the value of anything, the one thing you can always do is multiply by 1, or essentially multiply and divide by the same thing. So since we've divided this polynomial by 2xy squared, you have to compensate for that by also multiplying it by 2xy squared, right? Because those 2xy squareds, they'd cancel out, I'd get right back to exactly where I started. I haven't changed the value of anything. All right, let's finish doing some of that simplification. So I'm going to leave that 2xy squared out front. And remember, if there's addition in the numerator, just in the numerator, I can actually split that addition up. So this would be 10x to the 5th y squared over 2xy squared. I'm going to add that to 4xy to the 6th over 2xy squared. Now we're going to fall back on those skills we learned in the exponent section to be able to simplify these out. So we're going to have 2xy squared still out front. This first term is going to become 5x to the 4th. And that second term is going to become 2y to the 4th. So whenever we're pulling the GCF out of a polynomial, essentially what we want to get to at the end is that we have the GCF out front, the way we have this 2xy squared out front, and then in parentheses we're going to have everything that's left over after we've divided out by that 2xy squared. So this is a tool that's going to come super in handy in that next video where we actually talk about what do we mean by factoring a polynomial.